Now we are going to start our discussion on a very important characteristic of complex valued functions. So it is the characteristic of continuity. Now the word continuity means that something is going continuously, without any gaps, without any holes, without any jumps. So there are many phenomena around us which are continuous. There are many, for example, let's say consider the trajectory of a flying bird. Now, if you observe the trajectory, the path that the bird follows when it's flying, it is basically a continuous path. There are no breaks, there are no jumps, there are no holes in that trajectory. Similarly, when someone is speaking, so the sound wave is continuous. So that's why you can hear some other person. Now, for example, if you are talking on a mobile phone and if there is a signal break, then there will be a discontinuity in the sound wave. And that's why it will disturb your conversation. Now, the moment you are listening to me, it's basically the sound waves are approaching you in a very continuous way. So this procedure is basically consists of two steps. So in the first step, this machine in front of me captures the sound waves with little intervals. So for example, in a second, it will capture my sound with very, very tiny intervals. So in other words, it will have some discontinuities. But in the next step, which is the second step, an important step, now this data will be converted into a continuous sound wave. And that's why you can listen to me in a very smooth way. And similarly, we can find many, many other examples around us which are either continuous or discontinuous. Of course, if we observe some quantities around us, quantities which depend on other quantities, then we want to know that whether this quantity depends continuously on the second quantity or not. Now, of course, one of the important continuous quantity around us is time, which is independent quantity. And if there is a little break in time, then it would mean a big disaster. Okay? Now, let's go ahead and try to mathematically define what is continuity of complex valued function. But before that, our first observation is continuity means no breaks and no sudden jumps and no holes at any point. And of course, we are going to take the spirit of this sentence into the mathematics world, into the continuity of complex valued functions. So in mathematics, continuous function also has similar kind of definition. So what does it mean? It means, let's again observe that example of a trajectory of flying bird. So if you say that the trajectory or the motion of that flying bird depends on time. So as the time varies, then the position of that bird is varying. So it depends on time. And as you observe difference in time, or if you increase a little time, then it will change the position of the bird. Okay, so for example, if this is the trajectory of a flying bird, okay, so this is the bird, and it is basically a function of time. Now, the important thing to observe is if I change time, then the position will be changed, but it will not be a very big change. Okay, so it cannot happen that at time t1 the bird is over here, and after a very tiny interval of time the bird is over here with a big gap in the trajectory. Okay, so this is not possible. So in other words, first observation which will help us in trying to decide the mathematical definition of continuity is the small changes in the input of a function brings a small change in the output of that function. Okay, so let's start with a simple case of function of one variables. Of course, we can associate a function of one variable with a curve in two-dimensional plane. Okay, so let's say this is the graph of some function y is equal to f of x. Now, as you can see that there is a hole over here, so of course the path is not continuous at this point. And similarly, if you are at this point, then there is a big jump over here. So that's why the function is not continuous at this point. And if you are at this point, then once again there is a big jump over here and function is once again not continuous. So how do we how do we say that function is continuous at a point? Okay, so if you are at this point, then the function is continuous, because if you reach from either side along the graph of the function, then you reach at the same point and it is equal to the functional value at that point. So, but it is not the case in this point. So at this point, if you reach from this side and if you reach from this side, then you more or less reach at the same point, but the functional value is somewhere over up there. So that's why the function is not continuous. And similarly, at this point, if you reach from the right side, then you are around 4. And if you reach from this side, then you are at around -3. So even if you approach from either side along the graph of the function, then you are at different points. And of course, the functional value is totally different from these two positions. So what do we impose to make sure that the function is continuous? Of course, we make sure that if you are reaching from the right and left, then you reach at the same point, and that point is equal to the functional value. So in this case, the right side point is 4, and if you reach from left side, then reach at -3. If they are equal, so as in the case of -2, then still over here the function is not continuous, because the functional value is up over here. So that's why we impose 3 conditions, that if you approach from left side and right side, and you approach at the same point, and it is equal to the functional value, then we have a continuous function. Okay, so now approaching from right side and left side means we are calculating the limit, and if this limiting value, left hand limit and right hand limit, are equal, and if they are equal to the functional value, then we say that the function is continuous at that point. So in other words, the first condition should be the limit exists. So for example, the function is not continuous at this point because it doesn't satisfy this first condition. At this point, the left hand limit and right hand limit are not equal, so this point will be excluded. But this point -2 is still included because the limit exists. The left hand limit and right hand limit are the same. Now the second condition, once again, at -2, the functional value exists. Of course, it is not equal to the limiting value, but it exists. But it is not in the case of this point. Okay, so at this point, the function behavior is such that the functional value doesn't exist. So this point is excluded because it doesn't satisfy the second condition. But this point -2 satisfies these two conditions. But still we can see that there is a discontinuity. The function as a whole at this point, it is not continuous. So what do we impose then? So we impose that the functional value should be equal to the limiting value. And if all these 3 conditions are satisfied, then the function is continuous. And of course, now we can see that this point -2 is also not the point at which the function is continuous. Now, a function is said to be continuous on a set A if it is continuous at each and every point of A. Okay, so you can see from the definition that we are checking the continuity at a point. So continuity is basically the characteristic of a function at a point. So we check the continuity at x0. And of course, if we are saying that the function is continuous on a set A, then it should be continuous at each and every point of that set A. Now, since we are calculating the limit of a function at a point, so to calculate the limit of the function, we should know the function in some neighborhood of that point. Otherwise, we cannot calculate the limit at that point. Okay, so intuitively speaking, since we are saying that the left hand limit is if we are moving along the graph of the function, then at the point where we reach is basically the left hand limit. Now, if there is no graph in the neighborhood of -2, then you cannot move along the graph. So you should know the function in some neighborhood of a point if you want to calculate the limiting value at that point. And of course, the functional value can be calculated at a point, and if they are equal, the limiting value is equal to the functional value, then the function is continuous at that point. Now let's have a look at this example. We have a simple function and we want to check if it is a continuous function or not. So now let's see the continuity at point x is equal to 1. So first we want to calculate the limit of this function. So when x is equal to 1, then the part of the function that describes the output is basically this one, when x is greater than 0. So the limit of the function is basically equal to 1, and we can also see that f of 1 is also equal to 1. And since the limiting value is equal to the functional value, so we can say that this function f of x is continuous at point x is equal to 1. Now there is a very different point, which is x is equal to 0. So at 0 we are having this break between the two descriptions of this function. Okay, so the two parts of the function are basically have a break at x is equal to 0. So let's see if the function is continuous at this point or not. So what do we want to calculate? We want to calculate the limit when x approaches to 0 of this function. So to calculate this limit, we first calculate the left hand limit. Okay, so we are approaching the point from the left side. So if we are approaching the point from the left side, x approaches to 0 minus of this f of x. So when x is less than 0, we can see that the function is defined like x squared plus 1. So this is basically limit x approaches to 0 minus x squared plus 1. And in this case, we can see that the limit, left hand limit at point 0 is 1. And similarly, we can calculate the limit when x approaches to 0 positive of this function f of x. Now, it means that we are approaching to 0 through values greater than 0. And in this case, when x is greater than 0, the function is defined like x. Okay, so it means the limiting value becomes x approaches to 0 positive of x, which is equal to 0. And in this case, the left hand limit is 1, the right hand limit is 0, and the left hand limit is not equal to right hand limit, so the limit does not exist. So that's why the function not continuous at x is equal to 0. Now we can also observe this phenomena using the graph of the function. Now the graph of the function is something like this. So it's a parabola on this side, and on this side it is just a straight line. So after 0, so there is a hole, because at this point the function is defined like y is equal to x, and there is a hole because the 0 is not included in this part. Now we can easily observe that there is a big jump over here. Okay, so there is a big jump that we can observe in the graph of the function, and due to this jump the function is not continuous. And of course we can easily see that if we approach 0 along this part of the graph, then the left hand limit is 1, and if we approach along this part of the graph to 0, then we approach 0. So the left hand limit is 1 and the right hand limit is 0. So that's why the function is not continuous. Now let's carry on to the case of real functions of two variables. So if we are given a real valued function of two variables u of x, y, then on the same lines we impose the following conditions on a function to make it to be continuous function. So of course the limit should exist, and in the second condition we impose that the functional value exists, and the limiting value should be equal to the functional value. And if all these three conditions are satisfied, then the function is said to be continuous at point x naught, y naught. So once again, we are checking the continuity at a point. Okay? And if we want to say that the function is continuous on a set A, it means that the function is continuous at each and every point in the set A. Now let's try to solve this example. So if we want to check the continuity at point 0, 0, then we need to see three conditions. So the first condition, what is the limit when x, y approaches to 0, 0? The second condition, what is the functional value? And the third condition, whether these limiting value and functional values are equal or not. Now, from our previous discussions, we have calculated the limit of this function as x, y approaches to 0, 0, x cube over x square plus y square. In fact, we substituted x is equal to r cos theta and y is equal to r sin theta, and then we calculated this limit, and the answer was 0. And now, what is the functional value when xy is equal to 0, 0? So from this definition, we can see that when xy is 0, 0, then the functional value is 0. And we can easily see that the functional value is equal to the limiting value. So that's why the function of two variable uxy is continuous at point 0, 0. Now let's see the graph of this function. Now the graph of this function is this surface in three-dimensional space. Now this sheet is very continuous. It's very there is no break, there is no hole, there is no jump in this sheet. So that's why, and of course at 0, 0, at this point, there is no jump, there is no hole. So the function is continuous at that point 0, 0. Now let's carry our discussion to the case of complex valued function. So complex valued function, on the same lines, we impose three conditions to make it to be continuous at a point z0. So the first condition is the limiting value of the function should exist. So the second condition is the functional value should exist. And the third condition, of course, the limiting value should be equal to the functional value. Once again, it is the continuity at a point. We are checking the continuity at a point, and if we want to say that the function is continuous on a set A, then it should be continuous at each and every point in that set A. Now, let's check the continuity of this function f of z is equal to conjugate of z. Now, from our previous discussion, once again, we have calculated the following fact, that the limiting value of this function is equal to z0 bar. And of course, this, okay, so this is our from previous discussion. Okay, now of course, the functional value at a point z0 is also equal to z0 conjugate. So that's why this function f of z is continuous at z0. Now this z0 is just an arbitrary point of the complex plane. So that's why we can say that the function is continuous everywhere at each complex number. Okay. Now, the third part of the definition is basically saying that the limiting value should be equal to the functional value. It means the functional value should exist. Otherwise, we cannot check the equality. And the limiting value should also exist. Otherwise, once again, we cannot check the equality. So basically, if we just impose the third conditions, then the third condition basically implies the first and the second condition. So sometimes we can just consider this third part as the definition of continuity. In the third part, we are basically calculating, on one side we are calculating the limit of the function, and then we are saying that if this limiting value is equal to the functional value at that point, then the function is continuous. Now remember, how did we define the limit of a function? Okay, so the limit of a function as z approaches to z0, f of z is equal to L if this condition is satisfied. Okay, so what is the condition? For every epsilon, there exists delta such that the distance between f of z and L is less than epsilon whenever the distance between z and z0 is less than delta. So that's how we define this limit. Now, what is the difference between the definition of limit and the definition of continuity? So over here, the limiting value is any complex number L, but over here, this number is very special, and it is in fact the functional value at that point. So if we just replace this L with f of z0, then we will have another definition of continuity, which is known as the epsilon delta definition of continuity of f of z. Okay, so once again, we are just writing down the definition of the limit, but we are just replacing this L with f of z0. Okay, so rest of the definition is the same. For every epsilon there exists delta such that the distance between f of z and f of z naught is less than epsilon whenever the distance between z and z naught is less than delta. So we can say that the difference between the functional values and f of z naught is as small as we want as we approach this point z naught. Okay, so in other words, we can say that small changes in the domain around z naught would result small changes in the functional values around f of z naught. Now in this part, we discussed why we need continuity, and we described the continuity of function of one variables and then function of two variables, and then we defined what does it mean that a complex valued function is continuous. In fact, we gave two definitions of continuity of a complex valued function. In our further discussions, we will see the properties of continuous functions and its consequences